файл без названия.
Неопознанный пользователь открыл джам-файл без названия. Ну, хорошо.
Сейчас мы ему название дадим.
Да. Сейчас, но давайте тогда это самое... Можно пока рассказать краткое содержание предыдущей серии, или все были и все... Does it make sense to repeat what was shortly what was in the previous session, or everybody knows everything?
I didn't finish reading your note.
No, I bet only you read any notes. No?
Yes.
No, I also read Alexander's notes, so it's not true.
Yeah, but you don't count.
I haven't.
Yeah. So, but actually, there is one important thing. So, which I want to say, especially for Kolya. So we consider games, and we consider games of a strange form. So they are like von Neumann games with partial information. So to play like камень, ножницы, бумага, players play. Make their move independently, and then the moves are taken together, and the outcome is clear. But after the first game of this type, there is no payment, but we just determine what will be the next game. So, for example, if I win the first game, then the second time I get a simpler game, or vice versa, or whatever. So the games on the second level depend on what happened on the first level. And the real problem is the infinite series of this game. So we make infinite series of moves, and then in the limit there is a path, and there is a function, payment function, which depends on this path. But it's important, I think, for better understanding, to get what will happen after the finitely many games. So I will ask Kolya, so can you explain why this finite level game? So we have finite K games, and then we have a payment, which depends on the rules of this all the games. Why this final game, why this multi-level finite game has a cost, and how would you compute this cost?
We say value usually, but okay.
Not cost, but value. Value of the game.
In usual, yes. The answer is yes. It has a cost.
And how will you compute it?
Upside down. How you call
from
it?
Top to bottom, or from
bottom to top? From
so
bottom.
You consider the games on the last level.
Yes, and there is a cost already assigned to leaves, right?
Yeah, for leaves we have costs.
Then on the previous level you have some two-person game, von Neumann game.
Yeah,
and that will be the cost of this guy, and so
yeah,
on.
and so the last level you can like in chess, when they stop the game at some point, they just declare the cost after that without playing. So but there is some kind of thinking needed to understand why this is a kind of locality. So at the last step we should use the optimal strategy for the local von Neumann game, and this will be then we guarantee more or less the same as we get for this payment. And this is because the kind of linearity. So if we are already in this vertex, in our best interests is to move optimally in the remaining game, because it will be linearly taken into account when we go in the average for the total game. So is this clear?
I think it is.
But what other people will say? Is it clear or not?
Is it clear what should be clear?
No, should.
Yeah, and it is written in the text you shared.
But yeah, I don't know. Not Misha, if you are hearing, is it clear or not?
Миша, вот.
Ну, понятно ли, что для конечного числа уровней игра рассчитывается снизу вверх, и это без проблем?
You are asking me?
Я?
Question to which Misha?
Нет, Миша, который Андреев, это вы уже все читали, и не надо. Нет, я спрашиваю, который Миша Вялый.
I've also read your text.
Oh, so you are also invalid for testing. Okay. Then I just want to, if everybody. So what I want to say, only one thing, which we can, for infinite games, we can consider the same kind of functions. So for each finite level, we have some value, but then. And also we can have a local consistency. So the value for a given vertex is at most the expected value in this game, in this vertex, with the values from the next level. But then, since we don't have any last level, we have another condition that in the limit. For infinite branch, lim_inf, the payment is bounded by lim_inf. So this was called, how it was called?
Certificate.
Certificate, yeah. So certificate has two properties. Local consistency.
And how do you call the next property?
Don't know, I know, limit consistency or whatever.
Okay, limit consistency. The limit consistency, so this is like a definition of a means certificate, right?
Yeah.
Yeah, so and the limit consistency is that
Actual payment.
for every infinite branch,
Yeah.
which is, I don't know, a sequence of the nodes. F is our payment function, payer function, and F of omega should be well at
Less
most
or equal.
lim_inf of the value of our certificate along this branch. And yeah. So and then what we did the last time is we showed that there is a theory. Oh, okay, lemma. That
The natural strategy for min guarantees average payment at least C of C of root.
Yeah. So for any min certificate C, there exists a strategy of min such that average payment, this strategy guarantees that average payment is at most C of the root. Yeah.
And there was some kind of discussion. So so we can require lim_inf, or we can require lim_sup, or we can even require that it's less than lim in case the limit exists. Actually, the lemma will be true for all three versions. But for this more difficult ones, the one which is written there is the simplest one. For that, we don't need this martingale convergence, which we discussed. And for this, we just consider what is called fatu lemma. So we imagine that game is artificially stopped at nth level, then the average payment is bounded by C of root by this finite argument, and then we say that the integral of the lim_inf of functions is if all functions have integral less than C, then lim_inf also has integral less than C, and this is technically called Fatou lemma, but it's actually obvious because lim_inf is lim of inf starting from any level, and starting from any level we have function less than integral less than C because it's minimum of several functions, and then by limit convergence theorem it's also
All right.
So if the bottom line is that if we later will find that we will need a stronger version with lim_sup or lim, then we need to reconsider this martingale story. But if not, then we don't need this argument with martingales and can
I guess we will have to use this argument with martingales.
Okay.
But let's, let's solve our problems one by one. So when it comes, then okay, so then I can proceed. And I guess if you want to add something, please go ahead. But,
No. Let's see what will happen.
okay, so what remains to show, and it's the most substantial part of the theorem, is the following. So if there is no means certificate with
so now I think we will consider a gap, something like two different, because in the theorem we don't have a strategy for the real cost, real value. We just say that if it's smaller, then we can, and if it's bigger, then we can.
So what Lemma says is that there's no means certificate where the value of the certificate is x on the root. Then there is a max strategy. For any delta greater than 0, there is a max strategy guaranteeing
X minus 0.
X minus delta.
Delta, sorry. So more symmetrically, if there are a gap, so C1 and C2, either there is means certificate for C2 or there is max strategy for C1. And the question, this max strategy will be also provided in the form of a certificate or not?
So it will be provided in the form of the certificate. So let me say
we need a dual notion of certificate when
but it will not be dual in the sense that we also consider lim_inf here. Okay, so let me say, so max certificate, we need local consistency again
with reversed value of
so C of v should be the value of the game on its children with C as payments, the value of the game at v with C as payments as payf on the children. Okay, so that's similar, and global consistency will be that for any branch omega, now it should be at least lim-inf of, so f of n of omega is the value of the certificate on the nth level of the infinite of omega. So
Yeah, so actually this will correspond to lim sup of in the definition. So indeed for max we need the stronger version of certificate lemma.
yeah, so I mean the existence of such a certificate guarantees that if we use a natural strategy of max, the average payment is at least C of the root. But now we have to use this martingale convergence theorem, as they call it, Dup's theorem or something like that.
Yeah, but we can maybe skip this for now and then.
Yeah, so technically I will say that I will construct a max certificate where C of root is X, but for F plus delta function. But that's not terribly important now, but just okay. So
being pedantic, I would say that I originally assumed that f is the interval 0, 1. So, but it's not that important.
yeah. Okay, so let's let's try to do this. So on this step we will use Borel determinacy theorem, again by Martin. So in which way we will use it? Well, let me give you an idea. So
Sasha, wait a second. In the case of mean, we had required that lim-inf is less than f of omega, right?
is it
Yeah,
most.
but we could also require that lim sup.
And now we require that f is at least again lim-inf. So we require a weak condition for max, right?
For max, we require weak condition.
A weak condition.
Yeah, but still this weak condition is enough for us because we have Martingale's convergence theorem. So I mean, well, in these two, might say directions of this theorem, I guess inevitably you have to use this Martingale theorem in one of the two parts. So, okay, so what's the idea? Well, we know that there is no means certificate with C of the root equal X. How can you interpret this? Well, you can imagine that this means that if someone gives you some function on our tree and assume that this function is locally consistent for mean, then you can indicate some infinite branch of the tree where the global and if the value of the root is X, then you can indicate some infinite branch such that the global consistency is doesn't hold for this branch. So you can indicate some infinite branch where f of omega is greater than lim-inf.
So either we have a violation of local consistency or global consistency.
Yeah.
But you say it in the form that if the local consistency is okay, then there exists a branch when the global consistency is violated.
Yeah, Well, okay.
We can say like this, why not?
Yeah. So the idea is that how we will use Borel-determinants theorem. We will show that actually we can refute the existence of such a certificate in a, one might say, in a game or in an online fashion. What do I mean by that? I mean, let's say that mean mean doesn't, you know, reveal the whole certificate at once. Let's say, well, just by default we consider only functions that assign x to the root, and then assume that mean just tells me what are the values of the function on the children. I don't know, some values x1, xn. And then we first check, is it locally consistent at the root? And if it's okay, then I want to say where there will be then I want to immediately, without knowing what you will say next, what mean will say next, I want to indicate some child of the root where there will be an where there will be some global inconsistency.
So you consider a new game. So this first move in this new game is that mean suggests so there is infinite branching, continuum branching in the root, and the first move that we select the values of the certificate of the supposed certificate on all levels on all children of the root. Yeah.
Yeah. So mean selects values for
max. So mean selects value and max selects a suspicious place.
Yeah. So max max selects a child of the root, selects some v child of the root, where intuitively it says that there will be under v there will be some inconsistency global.
And mean is allowed to select only such values that the local condition holds, right?
Local consistent, yeah.
Local consistent.
I mean, if you can view it as if he selects something locally inconsistent, then he loses immediately.
Mm-hmm.
Yeah, but we don't need to do this. Just
so mean chooses locally consistent
extension of the certificate, and max selects any child when he doesn't believe.
Yeah. So he now only gives some values for this children, and max selects some child, and then they proceed. So
max doesn't select any values. Max just selects the child.
Max just selects a child, and so what? And so this, as a result, we get some infinite branch, and so max wins if this holds. So this is some game.
Hold with lim inf.
With lim inf.
Yeah.
And it's
so mean claim that
he
has a certificate. So if he was a real serious, then it should be less than lim inf.
Sorry?
No, I say that if mean has a certificate and follow this certificate, then the value f of omega will be less or equal than this lim inf, and so mean will win.
Yeah. So if we have equality, then mean wins. So the observation is that mean has a certificate. Well, basically, certificate it can be viewed as a winning strategy for mean in this game.
Oh,
Right.
just in both directions. So winning strategy is really what you will say if Max will select that child. So you need to be prepared for any selection of the Max.
Yeah. And you know, any infinite branch can appear as a result, right? Because Max has no restriction. He can choose any children and so on.
So I think this is a very, very important moment. So it's time to ask whether this is clear. Народ, понятно это или непонятно?
Нет, ну вроде что стратегия мина то же самое, что
Что нужно?
джихада.
Сейчас, I guess, Bruno, you understand this, yeah?
A bit of repetition would help.
Would help. Okay, so so there's a new game. The new game is just the online representation of a certificate. So min selects just
One might say it's like Max try and refute the existence of a certificate in an online fashion, and we just represent it as a game.
So min should show the certificate is somehow undisclosed, but on the min should disclose the next layer, and then Max should select one point where he doesn't or she doesn't believe min, and then min should disclose what happens below this layer.
Yeah, and in the inequality in the middle, f omega is larger.
It's just the negation of what is needed for min certificate.
Yeah.
So Max
Fn
win
should be Cn, right? Fn should be Cn, the value of the certificate at the nth layer.
Yeah, but I think that Fn is just a certificate on nth layer.
Yeah, and f is the
F is payment function.
Yeah, so it's better confusing.
Better to have different. So
yeah.
I mean, it's Sasha's fault because it's in his notes.
Okay.
No, you cannot say this. You are responsible for my notes if you follow the notation. Okay. Anyway, it's clear. But what was not so it's obvious that if min has a certificate, then it's winning strategy. But the less obvious remark, which is also obvious, but still less obvious, that just the strategies in this game is no more and no less than a certificate. Because the strategy should tell us what should we do for all possible moves of Max. So we should disclose the costs, the values of the certificate for the children on the first level, and then we should be ready to answer any move of Max. A strategy should provide us instructions what to do if Max will choose that vertex.
Okay, so we have equivalence.
Yeah, so if we are ready to provide answers for all possible behaviors of Max, for all possible selections of Max, then essentially we should have in mind the full function.
Okay.
So if I don't know, online, if I have a kind of online map when I am ready to show any fragment, then my strategy for playing this game is just an offline map, a full set of values for all vertices. No?
Yeah, I think so. So that means that in the original game, one of the two players has a winning strategy.
Not the original game. Either min has a certificate, and this is what we know, and we know already the consequences of this.
Yeah.
Or Max has a strategy of something different, of a type which we never considered before.
Yeah.
Or so like
I mean, in this auxiliary game, I would like to, so what I would like to say is that in this auxiliary game, either of the players has a winning strategy.
Yeah.
And since we are now considering the case that Min has no certificate, then I would like to say then Max has a winning strategy in this auxiliary, like I say, I don't know, let's call it refutation game.
But
to say
there is
like
some
this,
small thing which we should look. So this new game has a kind of another set of paths. There are somehow they consist also of choices of the certificate.
yeah, I mean, to say that either of the players has a winning strategy in the first place, I would like to say that this game is Borel, and then I can use
so it's
Borel's.
a bit different game than the initial game because it also includes other moves. When Min selects,
I mean, it looks like this. There is a continuous branching for the first, for this we have continuously many possible moves of Min at the first, and then finally many moves for Max, and then again continuously many moves for Min, and finally many for Max, and so on.
and only the moves on the second type are taken into account for payments.
Yeah.
And so we get a Borel function because
I mean, I guess no. I mean, values. What you select here is also matters. I mean, because
So we consider that one Borel function is bigger than other Borel function.
Yeah. And
I
mean, the idea is that why this condition is Borel? Well, I kind of want to say that this thing is Borel, lim is something Borel, and then on this strange tree where I can have an alternation of continuous branching and finite branching, this condition is also Borel. I mean, that doesn't sound like something improbable. That I don't know. It can be left as an exercise.
If we have two Borel functions, then their pair is also a Borel function. Yeah. And so we take a preimage of the half plane with respect to the pair of this function, and this is a Borel set.
Yeah. Okay, so in this case, we will now use our a winning strategy of Max in this refutation game to construct a certificate for Max.
For some smaller value of cost.
Yeah, I mean, let's not pay attention at these tiny details as of now. I mean, as I said, I will construct a certificate for a function. Well, I will have x in the root, but the certificate will be for a slightly greater function, for f plus delta. So it will guarantee that f plus delta is at least f.
Yeah, it will be guaranteed just something slightly weaker.
Yeah.
Okay, but now we have some strange thing. Let's think a bit before you tell us. Let's think about the problem. So somehow we know what should Max, which child Max should choose as an answer to any set of values.
Yeah. So let's please tell us now what will be a certificate for the children.
But we need not select one child as a response to something.
Yeah. So
select something for every child.
Yeah.
Ah.
So and you can tell us what we should select, for example, with this thing.
So for every family of valuations, we have something, and then we should.
And we should then assign something.
I have I have two words that come to my mind, but I cannot make any sense of any of them. The first is duality, and the second is fixed point. But I cannot explain what could be meant by this.
But what we are discussing now,
So
I'm
we have
already
a
lost.
strategy in this news auxiliary game.
Okay,
And
Max
we are
has a
trying
strategy.
we need to convert it to certificate for Max. So now we know that for every locally consistent things, which mean gives us, Max selects something. And instead of that, we should, by ourselves, select some other values for every child. So we need, it's a difficult task because we have some discrete information of unknown origin, and we need to produce continuous locally consistent valuation.
So we want to select something for all these 4 nodes, right?
Yeah. Yeah. You should assign something to each of these 4 nodes. Yeah. Some real number.
Some real numbers.
And what you know is that if mean has some, it gives you some function x on the children, which is consistent, locally consistent. I mean, let's say c, some function c on the children, which is locally consistent with x. It means that the x is at least the value. Then in response, you give to this function some child. Okay?
But the property, I mean, the winning condition for Max is asymptotical.
Asymptotic,
right?
yeah. So no guarantees from anything.
So how can we convert something asymptotical to something
No, but also if mean makes some asymptotic condition is not asymptotic in the sense that Max can choose something wrong and then still win, because if he makes a choice on the first level, this choice affects all the future, so it's not so asymptotic somehow. You cannot say that now we play as we want and later we will see. We should care from the beginning of what is happening.
Okay, anyway, so I can now reveal.
But maybe somebody, unlike me, can explain seriously what is.
Yeah, I mean, yeah.
How to construct the certificate from Max. Misha, totally другой.
We should assign V something to V.
We not need to assign things for the vertex. No, we can try to see take all possible assignments for min when this vertex was chosen, and then do something with the costs of this.
So what we should, so we consider the set of all means moves, so all means assignments of the children, such that Max goes to V in response to C.
Yeah. No, but this is a stupid thing which I just threw because I have no better. But you mean that we really should?
It's a great thing. But so what we do with it? I mean, let me give you some intuition. Like, what is harder if, let's say, the greater. So, what is the winning condition for Max? Let's recall that once again. So, f of v should be greater than lim of the values of the certificate that min gives on this infinite branch. So I mean, the greater, so the larger are values is the value of the certificate in a certain node, the harder is to play in this node, right? So I mean,
for max certificate.
we have no max certificate yet. We have this refutation game.
Yeah.
Where min undisclosed reveals the values of the certificate, you know, layer by layer. Well,
Yeah.
you know, when it gives you some numbers, you would like to choose a smaller number to go to, because the greater are these numbers, you know.
So you are thinking now as you were max, yeah?
Yeah. For max, you know, the greater are this number, the harder is to satisfy the winning condition for max.
No, I don't think so, because it depends on the function f.
Yeah, it also, well, yeah, it depends. So you can actually, so there's some trade-off. So min can give you some two numbers here. I don't know, x, let's say 0.7 and 0.5. It might be harder to go here because this is 0.7. So this number is larger. So min maybe will be larger, but still you may choose to go here because the function f is bigger here. So it will be easier here because this will be bigger. I just give you some, I'm just trying to give you some intuition what is happening. But, you know, the idea is that to assign something to V, to a child V, we should consider indeed all moves of min in response to which max goes to V. And obviously we would like to actually consider what, so we consider all C's, all moves of min in response to which max goes to V, and we consider the values of V on these, on V, the value of C on V.
So if so the more was the value of C of V,
yeah. So the more the value of V is, then it is each time harder for max to it's harder to max to go to V. I mean, it's less profitable for max to go to V, but still there is some maximal or rather supreme value for V, such that still max goes to V if min gives you something where C of V equals this. So what just I would like to say that actually I would like to assign this thing. Take all means responses or all means moves such that in response to which max goes to V, and then I take the supremum of C of V over these C's.
Okay, it's more or less clear why, like, if this C are locally consistent, then it's like it's clear why it's globally consistent, just because max wins in the game, whatever you choose.
Yeah.
Okay, so Bruno, do you see what is happening or not? If yes, maybe
I didn't prove anything.
No. Just why?
I just defined.
Just what is up to now? What is defined?
Yeah. So explanation. Yeah, that's clear. It's just a formula. You can understand it. So.
But just repeat then maybe I'll understand better.
So now we want to construct strategy, a certificate for Max in original Blackwell game.
Yeah.
And so we have to assign value CV to every node. And the formula is there. So we look to the auxiliary game, and then we will ask for all tuples which node is selected. So how do we select? So we do it inductively on the depth of the tree. And how do we select the value of a child? We ask the strategy for all tuples when this child is selected, and then we take the supremum. And so it's just, if I understand it correctly, that's the formula that's written here.
But why we do this?
No,
Kind of
this is not
motivation.
clear, but okay, I'm working on
I
it.
don't know.
So
You came up with this idea that we should consider all tuples of mean on the children of the root.
So let's look at this. So for some reasons, Max selects given vertex V, but he can do it for different values of the certificate given on the previous step. And what you say that the more the value is, then there are less reason to select these vertices. The more we are required to do, yeah?
Yeah. Well,
no, I think the intuition is clear. So Max knows that he wins using that strategy. That is, the value of f is larger than lim_inf. And that happens for all the moves over mean. In particular, for that moves for which the max supremum is attained, say.
Yeah, but here we have like a small kind of cheating. When we say max goes to V in response to C, we assume that C is indeed locally consistent.
Yeah,
so
yeah, sure, yeah.
So like,
I mean, means we allow, yeah, I mean, sorry.
No. The moves of mean are locally consistent by construction.
Yeah, but to, like when we say max goes to, okay, but so.
No, it's not obvious why our certificate will be locally consistent.
Yeah.
But this is.
So we have to show that X is at least the value, no, I guess for max, we should show that X is at most the value of the game with these supremums. I mean, okay, so, and this will be local consistency for max. But let me tell you one thing is that actually there might be, this supremum might be undefined. So there might be no C's, no tuples such that max goes to V for some nodes.
No, but then probably it's minus infinity.
Then it's 0.
No, okay, if between 0 and 1, then it's 0.
Then we just assign 0. Okay, let's try to prove it. We are trying to prove this thing, which is local consistency for max. Well, assume.
Yeah, strictly speaking, now we consider only the top level, for example.
Yeah.
And then we need to discuss
we are now considering the top level.
Yeah.
Just so assume for contradiction that X is larger than the value. Okay, now what I want to do is that, well, X is greater than the value of some game. Now, if I just increase you know, all the if I so I have some matrix, and in it I have some payments, and if I increase every payment by a little, by some small epsilon, then I still then X will still be greater than the value of the game. right? Because continuity. So
Not the continuity, just if you add epsilon to every value, then the game is also added by epsilon.
There's some technical details here. Okay, let's try to finish this argument. So assume that I add epsilon to everything, and then I still it gives me some tuple for children, and still x is greater than the value of the game with this epsilon shifted tuple. The value, it means that this epsilon shifted tuple is a valid move for mean in the auxiliary game, in the refutation game.
So say again. So if x is greater than the value of the original game, then mean has strategy.
Let's say x is greater than the value of the game with subs.
Yeah.
And then x is greater than the value of the game with subs plus epsilon. And then this supremums plus epsilon is a valid move of mean in the auxiliary game.
So you say that if new game has bigger value, then we can consider an encounter strategy. No, if the new game has small value, then we can consider the counter strategy for mean in this new game, yeah? And then consider this as a strategy in the original game and take a counter move of max. That's what you're saying.
Yeah. Then, so since this is a valid move of mean in the auxiliary game, there is some counter move of max. Let's say to v. It's v. But then there is a contradiction because.
But wait. Why
v?
Why this move is to v?
Well, it's some move of. I mean.
So some other node. Maybe.
I mean, it's some node. It's some child of some child.
You have fixed v before.
I didn't fix v. I defined for every v. I defined a real number which max assigns.
Okay. We haven't fixed v indeed. So to some child v.
Yeah. And then there is a contradiction because we have a valid move of mean. In response, we go to some v, but for this move of mean, the C of v is supremum plus epsilon. But this supremum is just, it's a supremum of all possible C of v's such that we go to v. So the idea is clear, right? Why?
No, you have just proved that it has that local property, right? Or what?
Yeah, I mean, there are some details here. The problem is that I can have somewhere, I can have one. Some supremums might be one for some children. And formally, I consider only those tuples of mean that where the values are from 0 to 1. So I cannot consider 1 plus epsilon.
But why did we need to restrict the values? Why don't we just ask for the game to be bounded, for the payment function to be
I
bounded,
don't know.
and forget about all this? It's
Bounded is for bounded convergence.
okay, but if the function is bounded, we do not care if
I mean, in any case, I would like to say that's not a big problem. So what I would like to say is that if it's 1, it's some supremum is 1, that let's not increase it at all. Still x will be greater than the value of the game, since we even don't increase some of the entries of the matrix at all.
But how we then obtain a contradiction? Assume that the
contradiction is that if we go, the contradiction is that because it is impossible to go to a child where mean to which mean assigns 1.
Why?
Because then mean has a winning strategy in the auxiliary game. Just assign once, always, to everything. Once you have assigned 1 to then if you assign 1 to something and max goes to this trap, then you can just assign ones forever later on, and you will win because f is at most 1. So, and your limit will be 1, and you will win.
So, I'm sorry. What were you explaining now? I am lost.
Sasha has explained what do we do if some value is 1.
Oh, but for this special case.
Yes.
Yeah. So I don't wanna. I mean, I don't. You're saying that like probably we can consider unbounded values of the certificates, but I'm not sure about that. I mean, let's be formal and let's try. So I'm insisting that means possible moves should be from 0 to 1 for every node.
Mm-hmm.
So that was a proof of well, what I just did. I just said what I'm doing. What is the max certificate for on the first level, right?
Yeah. So you suggested how you define the max certificate in the root.
No, not in the root, on the children of the root.
Yeah. On the first level. Yeah. In the root it's x. Yeah. For the first level.
Okay. Yeah. And then let me try to say what we do next. Oh, sorry, just a second. So now I'm doing. So I would like to now extend my max certificate further, right? So I take some child, of some node V, which is a child of the root, and I have assigned some.
And then you want to consider its children.
Yeah. So I have assigned some supremum to it. I have assigned the supremum of CV. Overall is such that V is a response to C. I don't know if it's clear. I guess already clear. So what I do next is I take from this set any, I take any move of mean, so I take any C such that C of V is, I don't know, delta half close to this supremum.
Oh, so the idea is that on the next level, we need to consider just two stages, and for that we need to fix some move of mean on the first
some
stage.
move of mean, because I want to eventually achieve global consistency, and to achieve global consistency, I need to use the fact that Max has a winning strategy in my additional refutation game.
Yeah, so if there were not a supremum but the maximum, you just consider the move of mean, which leads to this maximal, has this maximal value. But since we don't have a maximum, we need some approximation, and this approximation should be chosen, I guess, that on the all levels together, we don't get too much slack.
Yeah. So and then I take this C and I do the same, where instead of X, I consider this C of V here. And then I again, like for each child of V, I define like the maximal, the maximal number such that I go to this child when mean gives me this number for this child.
So like we take something like C0 of V, like we take C0, which is delta half close to the supremum, then we take then we continue our game with C0 as a first step, right?
Yeah. Sure. Yeah, so I can say.
So we just fix our first step C0 and consider only what happens after this first C0 move, yeah?
Yeah. And then, I consider now these supremums like I'm assuming from now on that the first move of the refutation game is C0, and then by assuming that I consider for each of these three nodes, I consider the supremum of all values such that I go to this, max goes to this node when mean assigns, gives a tuple where, I don't know, where.
So you just do
I
exactly
assign
the
here
same.
some supremum of all P of U, such that max goes to U after C0 and C. So that's what I assign to you.
And then you say that you can repeat the same arguments for these things, but with delta over 2, and then you do the same with delta over 4. And in the limit, you have whatever you want, and nothing else is needed.
Yeah. Well, I should also say one. For completeness, I should also say something that it might be that here is 0. I mean, what should I do if I never go? What I should do? Like, I don't know, in T, if I never go in T in the refutation game. So I don't have this C0 for this T at all. Do you like?
So you need some kind of minus infinity or 0, but now you have delta over 2, so there is maybe
No. I mean, there is no problem at all, because for these nodes where to which I never go, where I never go, I have assigned 0. I gave them 0 to this node. And then if you know, then max, as a max certificate, when you have 0 somewhere, you can just set 0 everywhere. It will be locally consistent, and you will have f is greater than, is at least than lim_inf.
Yeah.
You know, we now forget about the fact that Max can win in the refutation game, where he actually has a stronger condition that f is greater than lim_inf. But once we got 0, we can just forget about the refutation, about the auxiliary game, and then set and then put zeros everywhere below. And you know, it's again a trivial thing. The less you have, the easier it for Max to obtain a certificate. And if you have 0, it's like the simplest thing. So yeah, so that's something like this. So there are maybe some. I was not so precise as of now about these deltas, but we can try to. I don't know if.
Okay, let me try to repeat the entire structure. So the first, we have a notion of certificate, and second, we consider an auxiliary game when min suggests a certificate and max suggests a path. And then we apply this Borel determinacy to this game.
Yeah.
And then from Max strategy in this game, we want to construct a certificate for Max.
Yeah.
And then you say that this selection is more, or certificate is more or less straightforward. You just choose what could be obtained in the games against different means, more or less.
Yeah.
And then you claim that general blah 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 about this without any new ideas, just show that this certificate up to two small technical things, that because we have supremum but cannot take it maximum, this is a problem, and the problem is solved by using approximation with better and better precision.
Yeah.
And second technical problem is that since we have zeros and the zeros are now shifted a bit and that's blah blah blah, then we need to somehow take care of this technical problem in some unclear to me but trivial way. And finally, we need to remember that in our original definition of certificate, we can use both weak and strong definitions with lim_inf and lim_sup, because now the certificate of Max has a weak definition, but still it's okay.
Yeah.
And so you claim that there is no hidden difficulties in this scheme. You should just need to meditate exactly what are the trivial blah 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 in each place, and then you get the correct proof without any additional troubles.
I mean, as far as I get it, there are no I mean, there are no some deadly troubles here. I mean, well, the problem. So I mean, the problem with zeros, as I said, that's not the problem at all, because if you got 0 everywhere, then somewhere, then you can just set zeros.
No, but we should think whether this is 0 after adding this delta or before adding this
Just
delta.
don't add
This is a kind of confusing.
Yeah, I would say there is a like one slightly trickier part.
Yeah.
That the thing about the supremum, like when you how you prove local consistency, you just say that okay, when I want to prove local consistency, I have to choose mean strategy. Mean strategy against which I will apply my maximum strategy, like the result.
Yeah.
Some kind of it's not so hard, but you still have to like go to one game and back to auxiliary game and back to original game. Like there is another hop.
No, I say it again from the beginning. I didn't get anything.
When you like you want to describe you want to build a certificate for max.
Yeah.
To do so, you have like this supreme definition.
Yeah.
And to prove that the supreme definition is locally correct,
yeah,
you have to like to do some like not really complicated, but still some kind of work with going to the auxiliary game, understanding what strategy we do, again fighting with zeros and ones if necessary. So there is like not complicated, but still some kind of work to do.
There's you just say there, if it's not locally consistent for max, then these supremums give you actually like a valid move of mean. Because if something is not locally consistent for max, then it's locally consistent for mean. Because it's just inequality in the other direction. And moreover, if it's not locally consistent for max, then it's not locally consistent even with some slack. So you can actually increase these supremums by some small epsilon. And still, this increased supremums give you a valid move of mean. And then there must be a response to it. Some node, some child to which max goes in response to this tuple of mean. But then since in this tuple we assign to this node something larger than the supremum for the corresponding child, this contradicts the definition of this supremum. And yeah, that's more or less it, but there was some technical problem because we could have that some supremums are ones, and we don't want to go beyond 0 and 1. And then I just say that I don't increase these supremums by epsilon. I just say my winning strategy in the refutation game just can never go to 1, because if it goes to 1, then it loses.
Yeah, okay. So now a question to Bruno and Kolya and
I have a question actually.
Sorry.
When we build this certificate for max, do we subtract something from the initial x? Because I mean, on the first level, we have put these supremums, right?
Yeah.
This is already final values of the certificate on that level, or we will decrease them.
Yeah,
No,
let's actually decrease them by delta, and then
it's better to decrease function instead, so we can keep the supremum, so the value x, but in the final thing we will so this discrepancy will increase along the path, and finally it will be delta. But of course we can instead we can at the beginning add this epsilon to be sure that blah blah blah.
How do we
but still sorry so there is some supremum here, but then in some child, right, some supremum s, let's say that the s is assigned something to this child, and then from this child I proceed with some c0 such that c0 is s minus delta half, right? where C0 is some first valid move, it's some one possible first move of mean. And then I use here S minus delta over 2. And then I obtain that if I assign this, then I have that local consistency with S minus delta. Right? And so it means that it is, I think it is better first to assign S minus delta half to this. And then we have kind of local consistency, approximate local consistency. Then I know that the value here at every node is at most the value of the game on its children if I add some small delta to the values of the children. That's right.
No, but I really I cannot follow this argument. But what you are saying that you somehow guarantee by your reputation that there is no difficult problems, and if you do something what you should do trivial, then everything will be okay.
Yeah.
The argument is somehow confusing. So, but
I mean,
maybe
I
if
don't
we
know.
think,
I mean, if you just imagine that, I mean, is it clear if supremum, if you have just supremum is always attained somewhere, so we don't have these deltas, then is it clear? Just imagine this.
No, it seems to me that it's clear what you are doing, and this should be right. But whether it's trivially true or trivially false, it's not so obvious. One should think about this.
I don't know how to better solve this problem with deltas.
But it's quite convincing that they should not be a big problem. But because everything is somehow linear, if you add something in the cost, you add something in all the levels with the same delta. So generally, this delta should be easily transferable from every level layer to every other layer, and somehow.
Yeah, and looks like you can even achieve like maximum instead of supremum in some terms. So like if you're okay to lose some small amount on every level, then probably you can, like, instead of add, like,
No, you cannot have maximum if that doesn't exist maximum. I don't understand what you're saying.
You can, like, when you have supremum, you can have a point, like exactly this argument. If you're okay to sacrifice some small amount,
then you can achieve supremum by this precision, of course. Yeah. Okay, so Bruno, what you will say, is it convincing or not? Not really.
I can only agree with you. I want to like go over it many times until I feel better. But I have a question. Like you carry delta through the several levels. But is it possible when we look at the root, there is a delta, and then we apply compactness to get rid of delta while building the certificate and original game?
No, why compactness? We just we approximate supremum by element with precision delta over 2.
Yes, and then we decrease delta.
And then we not decrease delta. We just, and the next level, the precision is delta over 4.
Yeah.
On the next level, delta over 8, and the total slack will be delta.
Yeah. That's a plan. But
Yeah, but what is the problem?
So we're building a certificate for max, and certificate is for every delta, we get a different certificate.
Yeah. No, but we do not want to get something which is valid for every delta. We start
it's
with,
impossible. Yeah.
no, in the beginning we have some big gap, not big, but some fixed gap which we need to beat. And then we just take delta small enough so it's smaller than this gap.
Yeah. There is no hope to build a certificate that
And there was an example why it is, there is no hope.
For zero data.
Yeah. Okay, so Kolya, can it be made clearer, or it's good enough and cannot be done better?
I can't make it clear for sure, but for me it's convincing, right? So I'm convinced.
So you think that if you think about this a bit more, you can provide all the details which were missing, or
Exactly. That's my attitude now, right?
I mean, if you wish, I can try to provide the details. With
no,
this.
it will be much worse then. Please do not do this.
And just let me say very clearly. So where do we apply Martin theorem? It is on slide 3 when we say Min has a strategy if and only if Min has Min has a certificate. So on slide 3, if you go back in the middle, so where is the place where we use this big Martin theorem?
We know that Min has no certificate.
Yeah.
And then we know from Borel determinacy that Max had a strategy.
Yeah.
And then we convert this strategy into a certificate without any specific determinacy anymore.
Yeah.
We just...
It was not said clearly. I was a bit worried at this place.
Sorry. Here it's exactly And we should like formally argue, but maybe again some technical.
But
this winning condition is Borel once.
But because it's two limits, and when you say something is Borel, you're allowed to take limits.
Yeah.
So it's okay.
Yeah, and but the original proof of Blackwell was different.
The proof is by Martin, and it's more or less this, but I'm not. This is essentially, this is exactly it, but I don't know. In the rest of the arguments, he somehow, I don't know, for some reason, he considers some integrals, he considers some closed sets that approximate something.
Who considers, Martin or Blackwell?
Martin. Blackwell, it's no. The proof, it's Martin's theorem. Games are, the definition is due to Blackwell.
But Blackwell proved some kind of determinacy.
You said last time that he proved determinacy for sets for winning sets from the second level of Borel hierarchy.
But just reducing this to Martin determinacy for second level. He proved in some different way. Blackwell.
He first proved. I'm not sure that's Blackwell. You said it last time, I guess, or somebody. I can try to verify it. Somebody proved this for second level because that's already.
And we don't know how this proof goes.
I don't know.
Yeah.
I only know. I was trying to learn Martin, and
but even Martin
first
does
Martin
something.
Came up with some very hard proof. Then it very hard proof. Then it was some very hard proof. In 75, it was Martin with some very hard proof. Then Martin with very hard proof, and then everybody tries to learn this very hard proof, 85.
So you mean for Borel determinacy?
For Borel determinacy. I don't know. Nobody now pays attention to this proof for second level hierarchy because probably it's even harder than
But you say that even in the paper of Martin that you read, there are some integrals which you don't know why they are there and why they are for and what is happening.
Yeah, I mean, some integrals, some like closed sets, I don't know, on this last level, on this last step. Maybe he just reproved somehow the Martingale's convergence theorem, maybe.
But does he make an explicit reference to Martingale convergence theorem?
I mean, I have to verify.
No, if he does, it's strange that he reproves it.
I mean, maybe not. Maybe that's problem. I mean, I have to check it once again. So maybe I can even show it with some.
Okay, but meanwhile you're looking, I have a request. So there is another theorem which once I heard. Imagine that we have a game like in Martin determinacy game, but it's probabilistic. So in addition to some moves of Alice and Bob, there are also some random moves when we take randomly one of the two continuation of the game. And then there is some theorem, of course, then the game is probabilistic. So you should say that there is a strategy, you should prove that there is an optimal strategy, Borel, if it's Borel, there is an optimal strategy that guarantees a probability of winning at least this, or at most that. And
so we have a winning 0-1 winning condition, or what?
We have 0-1 winning condition, and we have also maybe with some epsilon slack that either there is a winning strategy for Alice with probability something minus epsilon, or there is a winning strategy for Bob for plus epsilon. So this kind of determinacy of probabilistic game, and it's probably as far as I remember, it's a consequence of theorem for Martin Borel game. So do you understand the statement? So we have a probabilistic game between Alice and Bob with random moves, and we want to prove that there are close to optimal strategies for both players.
Yeah, so the claim is either Alice has a strategy that achieves X, or Bob has a strategy that achieves X plus 1, X plus epsilon.
Yeah. No, in a reasonable sense, achieves that the probability of yeah. So kind of determines kind of Martin theorem for probabilistic games. And so my request is that the next time you explain us how the theorem is reduced to normal Borel determinacy, because if these games with Blackwell with the von Neumann are reducible, then I guess more or less all games should be reducible. And probabilistic games even looks better in terms of reduction.
Yeah.
So maybe you can. No, next time we have a.
You mean in some simpler way, yeah? You mean than for Blackwell games?
No, kind of are the same or simple or something like this.
I mean, Blackwell games include these games that you just described as a special case, then?
No, why? No, they don't have explicit probabilistic moves.
by the way, there is probably an answer to your theorem. Why? So you can just, yeah, okay. I mean, you can for this thing, you can say that, I guess we can consider just even more general games than Blackwell games, where when there is a pair of pure strategies, it gives actually distribution on the children. So, and your games are just when there is just one pair, or where there is just one distribution. And
so kind of, you say that this is first there is a kind of common denominator, then you can make even a better, a more difficult, more general kind of games which involve both classes. And also you claim that the argument can be easily applied to this.
Yeah.
But I'm confused. The original Martin games are not a subset of the Blackwell games, because I mean,
original Martin games can be seen as a subset of Blackwell games, but
yes,
yeah, I mean, in Blackwell
Martin
games
theorem,
we have only finitely many children.
But Martin theorem is not for equilibrium. The statement that we are using, one of the players has winning strategy, it's not with equilibrium.
No, there are no optimal strategies, but there is a cost, approximate cost, so to say. It's kind of this, of the same type of statement, but with not with exact cost, but approximate cost value. Sorry.
I'm confused.
No, von Neumann said that there is the value of the game, and just deterministic Martin theorem say that the value is either 0 or 1, so it's not so different. Oh, how we extend its result to stochastic game? That's what exactly I was asking. And who are this Matra and Sudarth? They are on your screen. We're reporting an observation of Matra and Sudarth. Who are they?
I don't know.
But what did they observe, at least?
I mean, I'm not ready to answer this yet. I have to think. I mean, as I was explaining, that you can, from this hard argument, you can use, determinacy of just stochastic games by considering even more general games than Blackwell games, and just applying the same argument. And I can just wave my hands and say that, okay, you can do the same thing as I did for Blackwell games. It doesn't really matter.
No, yeah.
Maybe it does matter. Sorry. No. I guess not. No, I guess not. Yeah, sorry.
Yeah.
Then
no,
the question is whether
I remember that when I asked Lyosha Chernov about this kind of probabilistic games, he told me that there is a general paper about Blackwell games which involves this, implies this, so it's just the paper you explained us.
Yeah. I mean, yeah, it's consistent with my understanding.
Yeah, okay. So maybe it's instructive for pedagogical reasons or propedeutical reasons to repeat the arguments for the case of probabilistic games to see how they work, and then what is the generalization or how it goes. But indeed, there are very complicated notation in this Martin's paper.
Yeah, I mean, if you write a paper, you have to, you cannot just, I mean, not everybody can just write papers with no formulas.
But they're very interesting. E minus, E plus, and F tilde.
I mean, yeah. I mean, so this argument so let me show this thing.
Most
It's very
frightening
complicated.
place.
The most frightening place. Yeah. So when I construct yes.
And what is why you need Lebesgue measurable? If everything is Borel, why is?
I don't know.
And there is some reference to some Verort. What is?
Oh, so there's the variations.
Variations, yeah.
Where was it?
I'm sorry, what are we doing now? We are reading the original paper?
No, we're trying to understand what is the connection with the probabilistic games.
I mean, if you're unhappy with that, I can stop it. Sorry.
Напугали.
Yeah,
Sorry.
I will go
Обидели.
because I have to check some urgent things.
Yeah, okay.
Bye.
Bye.
Thanks for
No,
that.
собственно, we are finished anyhow, but
Yeah, sorry. Yeah. I mean,
yeah.
I can stop sharing.
Yeah, so Andrei, maybe you can explain the next plans for the next week.
Okay, next week we have a talk in unusual time. It is 12:30 Moscow time, 2:30 of the French time, and
How past 10?
2:30.
No, if it's 12 Moscow time, then it should be 10 French time. No, it's very important.
Wait,
Just tell us exactly the time. It will be.
Нет, это очень сложный вопрос, я не могу быстро ответить, я уже быстро думать уже не могу. Нет, может быть, там в повестке все
Okay, the
неправильно
exact time will
написано.
be communicated later.
Нет, подождите, вот вы меня запутали, я сейчас ничего не могу делать, надо разобраться.
В повестке написаны консистентные вещи. В повестке написано 12:30 по Москве. Нет. 12:30 по Москве, 14:30 по Парижу. Так не бывает.
Так не бывает, да. Да.
Okay,
А как на самом деле?
Сейчас скажу.
Повестка
я посмотрю.
недействительна.
А
но-
повестки и не было. Разве была?
Во-первых, повестка была. Ну что вы думаете? Ну, по крайней мере, некоторые люди повестку получили, вот даже вот, я сейчас прочитаю. Да. Так, если вы говорите, что не бывает 12:30 в Москве и 14:30 в Париже.
Да.
Хорошо.
Но повестка была, да.
Да, значит, на самом деле 12:30 в Москве – это 10:30 в Париже, так что?
Да. Но вопрос в том, что, может быть, надо говорить 14:30 в Москве, 12:30 в Париже.
Нет,
Сейчас.
мы договаривались на 12, а потом принесли в 12:30.
Сейчас я скажу, это должно быть 17:30 в Гонконге. Давайте
Да,
это...
ну 5 часов разницы с Москвой.
Сейчас 12:30 Москва, Конг. Вот, сейчас я... Значит, в Москве... Так,
Yes. Moscow.
Значит, в Москве будет 12:30, в Гонконге 17:30, а в Париже, как
10:30.
мне объясняют, якобы 10:30. Ну, допустим.
Да. И
Вот.
там будет доказано утверждение о неразрешимости некоторой задачи, связанной с неравенствами про информацию. И в этом доказательстве будет чудесным образом использована неразрешимость задачи домино для тайлинга.
Да, но вообще по-хорошему хотелось бы доказать, что там множество неравенств для энтропии, ну, там, скажем, с рациональными коэффициентами неразрешимо. И эта задача не решена, по крайней мере, никто этого не утверждает. Но вот если вот эту задачу несколько обобщить, там, разрешить какие-то там нелинейные коэффициенты в правой части, или разрешить требовать, чтобы некоторые случайные величины были двоичными, то тогда якобы получается доказать неразрешимость. И для доказательства этого используется тот факт, что возможность замостить плоскость данными этими самыми плитками, тайл-сетами, плитками Ванга, она неразрешима. И это будет рассказывать некий, значит, товарищ из Гонконга, это, видимо, ученик известного нам Янга, который изобрел эти самые неклассические неравенства. Но где у него там имя, а где фамилия, это я в точности сказать не могу. У него там есть, вот у него имя и фамилия состоит из 3 слов, и где там что, это...
Да. Но это самое, и доклад будет исполняться на английском языке.
Вероятно, да.
Это хорошо. Могло быть хуже.
Нет, китайский, английский, это, я думаю,
Ну, Russian English is also not very clear.
not
Ну,
very
не
clear.
скажи.
For Russians, maybe it's clearer. But for Chinese, I guess the opposite is true. Вот. Хорошо, нет, как-то вообще как-то все не так страшно с этими играми. Оказалось, это надо еще обдумать, но какая-то тут свет в конце туннеля имеется.
Ну, это с этими оказалось не так страшно, а вот с Борелем-то это все-таки...
Нет, с Борелем вот... Нет, я когда даже это рассказывал, но вот сейчас я опять все забыл, и, может быть, это вы тоже как-нибудь расскажете, понятно так и доходчиво. Там вот это смысл этого накрытия какой-то загадочный, вот все бы это разъяснить народу желательно.
Нет, смысл накрытия разъяснить невозможно.
Ну уж прямо. Вы
Это,
подумайте.
ну, извините. Тут, как можно понять гениальных людей, которые придумали эти накрытия?
Ну, надо найти таких промежуточных товарищей, которые не такие умные, но все-таки еще могут понять. И постепенно так это редуцировать и
Ну,
переводить.
Понять, типа, понять...
Граждане, это хорошо все, но пора заканчивать.
Да, ладно, все.
Ага, до свидания.
До свидания.
Свидание.
Спасибо.